Here we're given a limit as n goes to infinity of the sum as I goes from 1 to n of x sub I times the square root of 1 plus x cubed, or x sub I cubed, times delta x. And we're given an interval from 2 to 5, and we are supposed to express the limit as a definite integral. So we're looking at the integral from 2 to 5. That's where the 2 and 5 go. And this is going to be f of x. So f of x sub I, based on looking at this sigma, is x sub I times the square root of 1 plus x sub I cubed, which means that f of x is equal to x times the square root of 1 plus x cubed. That thing is what goes into the integral. So the integral from 2 to 5 of x times the square root of 1 plus x cubed. The delta x here becomes dx, our differential for the integral. And that's it. What we did there is basically translating. Now there are properties of the definite integral. I know this is a lot to look at. The first one says that I can reverse the limits of integration, AB, BA, as long as I make the result negative. If the upper and lower limits match, the integral from a to a of anything is 0. Well, there's no width, if you think about things in terms of rectangles. The third one is that the integral of a constant from a to b is c times b minus a. And if you think about this in terms of a graph, it should make perfect sense. If this is c and then this is a and this is b, all I have is the area of a rectangle, right? The fourth one says that if I have two functions in the same integral, then I can split it up into two separate integrals. I don't do that very much. The next example, it will show like why we need to know that. It will be useful, but generally speaking in practice, I see this from students, in my opinion, way too much. Generally, I recommend writing as few integral symbols as possible. Fifth one says that if I have a constant, I can pull it out of an integral. That should make sense if you think about an integral as a sum of a bunch of terms. The last one is kind of interesting. It says that if I have an integral of f from a to b overall, then if I have some other number c, and get this, c doesn't even have to be between a and b, but I'm going to put it between a and b for sanity's sake. It says, this last property says that I can split up the integral from a to b by considering the integral from a to c and adding that to the integral from b to c. In terms of areas, this should make perfect sense. We don't actually use all of these a whole lot, but they are useful to know. One that we kind of do use is switching limits of integration. Just make sure that you know that means you're going to put a minus sign out front. And then this whole factoring out the c thing, pulling it out in front of the integral, that's kind of common. But like I said, I have an example where we're going to use this one where we can split up a sum of two functions into, or I should say, we can split up the integral of a sum of two functions into the sum of two integrals. And here we're presented with evaluate an integral by interpreting it in terms of areas. And we have the integral from -5 to 5 of x minus the square root of x squared, x minus the square root of 25 minus x squared dx. Notice this integral has two terms, x and the negative square root of 25 minus x squared. That means we have parentheses around the terms because they're being multiplied by dx. Using this property, we're going to write this as two separate integrals. So I'm going to say this is the integral from -5 to 5 of x minus, x dx. Don't ever forget the dx. It's very important. Minus the integral from -5 to 5 of the square root of 25 minus x squared dx. Now we can use the limit definition for the first one if we wanted, but we actually can't because we're supposed to interpret in terms of areas. We would not be able to use the limit definition for the one with the square root. So it's a good thing we're thinking of things in terms of areas. The first one is the function is y equals x, or f of x equals x, from -5 to 5. It will make a lot of sense, I think, if you've been following along, that from 0 to 5, I have a triangle that has a base of 5 and a height of 5 because y equals x. And so the area of this triangle is equal to 1/2 times 5 times 5, or 25 over 2. What may make less sense is that over to the left of 0, I mean, I have a triangle that's the same size, but the function values are negative. I mean, the area of the triangle is still 25 over 2, but the integral from -5 to 0 of x dx is -25 over 2. The reason is, if you think about function values, all the function values are negative. Well, that pointer doesn't work. All the function values below the x-axis are negative. And so if I'm thinking function value times width, they'll all be negative. The result is that this first integral evaluates to 0. The -25 over 2 exactly offsets the positive 25 over 2. Now let's look at the other one. If we're thinking of f of x is equal to the square root of 25 minus x squared, it might be easier to think about y is equal to the square root of 25 minus x squared. And if you don't know what this shape is right away, then sometimes it's good to play with an equation. Let's square both sides, see what happens. Y squared equals 25 minus x squared. Hey, let's put x and y on the same side. X squared plus y squared is equal to 25. Well, no, that's a circle of radius 5. And it's half of a circle of radius 5 for the function. The area of the circle is pi r squared, so 25 pi. But we have an area of a half circle, and so it should be 25 pi over 2. Back to what we had here, the integral from -5 to 5 of x dx is 0, and then we had a minus, so I'm going to put a minus here. And then we have 25 pi over 2. And so the result is -25 pi over 2. And this may be really confusing because we were told something about areas. We were told to interpret it in terms of areas. So I get a value for the first integral, which I really kind of ended up splitting -5 to 5 into -5 to 0 and then 0 to 5. But they zeroed out. And then minus the area of half a circle. So if I subtract two numbers and it turns out to be negative, hey, it's negative.